Today's video will be going over exponential functions with rates. A rate is a percentage of growth or decay when we are referring to exponential functions. Now for the new formula that we're using, instead of just having some value b on the inside, which was our factor, we now have 1 plus or minus the rate in which we are changing, depending on if it is a growth, positive, or decay, negative. B originally was that factor. Now we can say, like I stated, we add 1 in order for it to be a growth, or we subtract from 1 in order to be a decay. So if we use this in a couple examples, example 1, in 1990 the population of Washington, D.C. was about 604,000 people. Since then, the population has decreased about 1.3% per year. What is the population in 2017 if this trend continues? So if we look back at our original equation, we need a starting value, we need a rate of change, and then we can figure out what our b is, our actual factor is. So if we look at this, the problem states in 1990, the population was 604,000 people. So this would be our start. Now our rate states that it decreases 1.3%. So the decrease means that we are going to be subtracting from 1. And to change a percent to a decimal, we just move the decimal place over 2 positions, giving us 0.013. And all this is still going to be raised to the power of x. So if we were to fill this out as we go, our initial value, as we stated, was 604,000. This is a decay as we are decreasing. Our rate was 1.3%, which means that our factor is now going to be 1 minus 0.013. Let's make sure I do this correct. Look at there, nice and easy. So our factor is 0.987. So if we clean up our factor to write our function notation form, we still have the 604,000. We can just write the simplified version, which is what we're used to now, and we still raise it to the power of x. There's nothing that shifts this, so we still keep our same asymptote equation. It'll always stay y equals 0 until we actually learn about shifting the exponential function. Now, it asks for what the population is in 2017. So if we go from 1990 to 2017, that is a total of 27 years. So we would replace x, or substitute 27 in for x. Now, this will give us a decimal in our answer, so we must round this. Our population, if we follow this track, would be 424,228 people. Now, we can't have parts of people, and we want to round down in this situation. I can get my mouse back. There we go. Example 2, a city population increases by 4% each year. If the current population is 235,000, what is the population in 30 years? So if we look at this, our starting value, which is what it is currently, is 235,000. This is increasing, so this will be a growth. The rate in which it increases is 4%, which, let me make sure I'm following along, correct. Which, by the way, let's make sure that we understand that this is a percentage. So our factor in this situation would be 1 minus 0.4, which would give us 0.96. So following the same setup that we had earlier, creating our equation, we have our function notation, a function of x equals the starting value times our factor, which we simplified from the rate, to the power of x. Yet again, nothing that's shifting our exponential function. We didn't learn that yet, so this is still going to be a y equals 0 for our asymptote equation. Now it's asking for the population in 30 years. It's giving us the value in which we plug in for x, which we substitute in for x. So this would be 762,198 people. Now, just going from raw data, such as a table, you can break some of this down relatively quickly. We know that the starting value is when our x value is 0. So just mark example 4 already. That means that our y value, the 64, is where we're starting at. Now the easiest way to figure out what your factor is dividing our value at 1, the 32, by our starting point. And then we can check to see if that factor works with all of them. In this case, this is 1/2. A half of 64 is 32. Half of 32 is 64, so on and so forth. So we know that this rate works. Now for our b, I'm sorry. Oh, that's right. Now our b is just a half value. We already dealt with this. I almost confused myself there. Both our factor and our rate are the same value because it's the halfway mark of 1. So it makes it real easy on this one. To create the equation, f of x equals the starting value, 64, multiplied by the factor, 1/2, to the power of x. Now if we wanted to find out what the function of 12 equals, we would plug in 12 for our x, which would give us 0.0156 rounded. We can do the same process on the other side. 15.45 divided by 15. Sorry, the screen I'm using is shaking. This will give us a decimal of 0.03, which would have been 3% increase. So if we look at this, our starting value was 15. I'm sorry, I'm a little off here. 1.03 is what 15.45 divided by 15 is. This gives us a rate of 0.03. And our factor is just 1.03. So we need to remember that B is standing for the factor, whereas R is standing for the rate, what we are adding or subtracting to 1. So if we plug this into our original equation, we have the function of x is equal to the starting value, 15, times the factor, 1.03, all raised to the power of x. Same way, we plug in our value of 12 in for x, and we will get a value of 21.3864. So all of this work is doing the same process. We're taking our equation and plugging in the values that were given from a problem in order to solve for a specific y value, a specific output. We have our initial value, our starting value. We have the factor, which is created by 1 plus or minus the rate, depending on if it is a growth or decay. And it's all raised to the power of x, which is how much time has passed normally.